Hello, we're now going to discuss the intermediate value theorem. Let a be less than b and let f be a function from the closed interval ab into the reals such that f is continuous on the closed interval ab and such that f of a times f of b is negative. In other words, f of a and f of b have opposite signs. They're non-zero and they have opposite signs, in fact. Then there exists a real number c on the open interval ab such that f of c equals 0. And instead of an intermediate value theorem is good, sometimes I shorten it to IVT just to save myself some headache. So now there is an IVT for open intervals. I'm not really going to use it much, but here it is. It's analogous to the closed interval, and it just requires a little more tender love and care. Let a be less than b and let f be a function from the open interval ab into R such that f is continuous on this open interval and such that the limit, since f of a is not defined, we have to do it this way, such that the limit as x goes to a from the right of f of x and the limit as x goes to b from the left of f of x, so x is coming into a from the right, x is coming into b from the left on the other hand, such that these two limits both exist, are non-zero, and have opposite signs. Then there will exist a c on this open interval such that f of c equals 0. Now guys, a linchpin here is that f is continuous. That's important for both of these. These are pretty much cousins of each other. The open one just allows us a little more freedom. The closed one, though, is pretty much the one I'm going to be using. The open one allows a little bit of generality, I guess, but never mind that. It's just, let's just call it the IVT for open intervals. Let's just use this one for the, I think I pretty much just use this one all the time. This is the one you're going to see more of anyway, I'd be willing to wager. But anyway, this one's here if you ever need it, okay? So let's do an example. And let me scroll down and to the example. Here's my cursor. Let f be a function. Oops, I forgot my codomain. Sorry, guys. R. Hey, sorry about that. Let f be a function from the closed interval -4 to 3 into R such that f of x equals x to the fifth minus 4x squared plus 6. Then if you plug -4 into f, you'll get -4 to the fifth, which is -1024, and then minus 4 times positive 16, so you're minusing a positive 64, and the plus 6 is just stoic. It's right here. I went ahead and did the arithmetic already. I did PEMDAS, or please excuse my dear Aunt Sally, kind of arithmetic is what they call it. It's order of operations arithmetic, okay? And then that's equal to -1082, which is less than 0, while f of 3, on the other hand, is equal to, you plug 3 to the fifth power is 243, 3 squared is 9, 9 times 4 is 36 right here, and then plus 6, and that equals 213, which is greater than 0. The moral of the story is f of 4 is a negative number, f of -4 is a negative number, f of 3 happens to be a positive number. Okay, they're opposite signs. And you know what? F is continuous. It's a polynomial. And so we have to cross for some x value in between -4 and 3, we have, f of that x value has to be 0. We have to cross the x-axis, aka f of x, which is my y-coordinate, equals 0 for some x value between -4 and 3 on the open interval from -4 to 3. We know it's not the endpoints themselves. We've already checked. For some x in between -4 and 3, f of x equals 0, aka y equals 0, aka we're on the x-axis. So, okay, so again, we're just stating what we've already said. F of -4 and f of 3 have opposite signs. So, and f is continuous. So by the intermediate value theorem, there exists a c. I called it x a minute ago. In my writing here, I called it c. There exists a c in the closed interval such that f of c equals 0. Same thing. I was using the letter x a minute ago. Or here, let's just use letter c, okay? Just to be consistent, because I use c in the definition. So let C be my name tag, okay? So there exists a C by the intermediate value theorem. There is a C on -4 to 3 such that f of C equals 0. And really, I could have said open interval right here, but oh well. No harm done. So the point is, f was continuous. F of this endpoint had the opposite. F of -4 and f of 3 are opposite in sign, SIGN. F is continuous on the interval, so by the intermediate value theorem, there exists a C in between -4 and 3 such that f of C is 0. Think about it this way. F of -4 is below sea level in the sense that it's below the x-axis. F of 3 is above sea level and that it's above the x-axis. And if you're continuous, you have to trace out a continuous path. You can't quantum teleport, so to speak. You can't do any kind of discontinuous stuff at all. So you have, if you're continuous and and if you're above the x-axis at one x-coordinate and you're below the x-axis at another x-coordinate, somewhere in between, you're going to have to cross that x-axis because you're continuous. There's no cheating or teleporting or anything like that. And by teleport, I mean discontinuity, by the way. But anyway. Notice, however, that the IVT tells us nothing about what C looks like. What does C equal? That's a hard thing to find in general. There's problems where it's not hard, but in general, finding C may not be an easy thing to do at all. In practice, finding C may be very hard. The generalized IVT for open intervals would work if we replaced this -4 or -4 to 3 with +4 to 3. It would have worked just as well. So if we would have left f of 4 and f of 3 undefined, but else defined f of x to be the same, we would have used the IVT for open intervals. And we would have got the same result. That's all for the intermediate value theorem. And there's problems where you can go in and actually solve for C. You're like, well, Jason, what does C equal? That's what we were just talking about. In general, it's very hard to find. You may have to use technology. But there are problems like with quadratics and all that where finding C is doable. Sometimes it's easy, but that's not generally the case. Let's move on to the squeeze theorem now. The squeeze theorem, suppose that A, C, and B are real numbers such that A is less than C, which is less than B, and suppose that D is a subset of the reals, but is a superset of this deleted closed interval right here. Now, whether C is in D, we don't know. It might be, it might not be. Next, suppose that F, G, and H are functions from D to R such that f of x is less than or equal to g of x, which is less than or equal to h of x for all x in D, and such that the f limit as x goes to C is equal to the h limit as x goes to C, which is equal to some real number L. Then it will be the case that the g limit will exist and it will equal L. So the g limit must exist and it must equal L, given all this up here. So the thing that's going on here is that for all x in my domain, for all x in my domain, G is trapped between F and H, okay? G is sandwiched. Some people call this the sandwich theorem. I'm calling it the squeeze theorem. But G is squeezed or sandwiched between F and H. And it makes sense, it sounds reasonable that as x zones in on C, that the G limit ought to be L if both of these two limits equal L. The G limit would just about have to be L, intuitively. And indeed it is the case. Now, I'm not going to prove this. This can be rigorously proven. I'm not going to do that. I'm just wanting you to take it for granted and we're going to use it. Okay? Here's an example. Take the limit as x goes to 0 of x times the sine of 1 over x. We claim that that limit is 0, and it is, but we need the squeeze theorem to justify. But why is this limit 0? Because, here, let's do a squeeze. We can, x times the sine of 1 over x. Here's the thing. Let's just consider our domain to be all non-zero real numbers. Everybody but 0, okay? So, notice that it is the case that negative absolute x is going to be less than or equal to x times sine 1 over x, which in turn is going to be less than or equal to just ordinary absolute x. So this is negative 1 times absolute x. This is ordinary absolute x. And our function of interest right here, our f of x equals x sine 1 over x, it's caged in between these. Okay? And the non-zero reals, that is our domain. And so the limit as x goes to 0, but we already know, but, okay, not so, excuse me, back up. This is true because this is caged between these two for d equals the non-zero reals, and because the limit x goes to 0 of these two guys here obviously equals 0. Remember, absolute value is continuous also, but we're assuming it to be continuous without proof. It and the polynomials and all those. So this limit squeezes to 0. My right extreme, this is my rightward extreme right here. As x goes to 0, it evidently goes to 0. Now, as x goes to 0, this left-hand extreme also goes to 0. So this guy caged in the middle would have to go to 0 by the squeeze theorem. So since this is true, and since this is true, our original guy here on the left is true by the squeeze theorem. Okay? Let's do another example. The limit x goes to 0 of x squared times the sine of 1 over x. Now this time it's x squared. I'm sticking in front instead of just x. We're doing a different example, of course. Again, this goes the way you think it ought to go. Now, we don't do parentheses here. This is the negative 1 times x squared. Indeed, this guy in the middle right here is caged between negative x squared and ordinary x squared. And the limit as x goes to 0 of x squared and negative x squared is obviously 0. So this guy right here and this guy right here, they both go to 0 as x goes to 0. So this guy in the middle has to go to 0 by the squeeze theorem. And so we get our final result is this. Okay. So that's an application of the squeeze theorem. And if that finishes the squeeze theorem, yeah, let's close the video out and we'll move on to the next video. Thank you guys. See you on the next video.